Welcome, mathematicians. Today we are going to be looking at an application of our right triangle theorem. We're going to be looking at interior diagonals. So our learning objective is right over here. So our goal, let's get a highlighter so we read this. Learning objective, we are learning to find the interior diagonals. I underlined that. I'm going to highlight it because that's some new vocab that we got there. Of three-dimensional shapes. Those are things that are existent in our world. They have at least three measurements to define them using the right triangle theorem. Let's get started by just reminding ourselves what that right triangle theorem is. This is our right triangle theorem. It is a squared plus b squared equals c squared, where c is the hypotenuse of a right triangle, a and b are the legs. So it's the sum, the square of the legs of a right triangle is equal to the square of the hypotenuse. We're going to be applying this to find diagonals. So an interior diagonal, we're going to go ahead and fill this in. If I gave myself enough room in here. An interior diagonal. I did not. That's okay. There's a line that connects two vertices or corners, you can think of that as, of different faces of a three-dimensional object. So interior diagonal is only talking about 3D things, and it is basically connecting one corner from something to an opposite corner. We're going to look at a couple examples. We're going to get started right away with this first example. So we have here a cylinder. You can see I've done my best to shade it so it looks real 3D. I have some measurements on it. An interior diagonal of this means that it needs to connect two of the faces together on opposite sides. You might notice that this cylinder doesn't really have a corner involved, so we're going to do our best. We kind of get to define it and then look at the opposite. However, it does need to connect opposite faces or different faces of it. So I'm going to use orange to make our diagonal. Notice that a cylinder only has two faces, the top and the bottom in this case. So I'm going to go from one corner down here, corner of course being loosely termed, but I want to stretch it all the way to the opposite side over here. So that orange line is our interior diagonal. So now we're going to kind of play with this. In order to find out the length of that interior diagonal, you might see already we kind of do have this loosely defined setup of a right triangle. Notice how I drew this, that orange makes the hypotenuse. It's a nice diagonal length. And if I kind of continue my triangle down the side here, where I put that light blue color, that could be one leg, and then I have to stretch it all the way across the bottom face, hopefully passing through the center. And that would be the last leg of what looks like a triangle. So I'm going to highlight that briefly in yellow. So here's my right triangle that I'm going to focus on in here. So already I can easily tell what one of those lengths is because I have right here, hey, the length of one of these legs is 5 meters. However, the length of this one I need to play with a little bit. Oh, I drew over my 3-meter marker right here, so I'll put that back in. However, knowing that that 3 meters is there, that means, hey, that's just actually the diameter of the circle that I just drew with my blue to make that leg. The diameter of a circle is twice the radius, so that tells me that, hey, this all the way across is going to be 3 times 2 equals 6 meters. So now I have one leg of 5 meters long, one leg of 6 meters long, and I want to find the hypotenuse, the orange right here. So let's go ahead and write that down. I'm going to put my legs in blue. So here's the setup using, of course, my right triangle theorem. A squared plus b squared equals c squared. Hypotenuse is orange. I'm going to plug in and solve. So one of my legs is 5 meters long. Ooh, that was a wacky 5. One of them is 6 meters long. I am searching for c squared. 5 times 5 is 25. 6 squared is 36. This is still equal to c squared. Add those two together. Ooh, what is this? 161? Hope so. Equals c squared. Remember that in order to undo a square or an exponent, we're going to have to take the root of it. So in this case, we're going to take the square root of both sides. Here we go, square root. Square root. Square root of 61 is not a perfect square. We can either leave it as it is, because you know what? This is an exact number right here. Square root of 61 equals the square root of 61. It's an irrational number, so we could try to make a guess of where it is, where it lies, especially that's a good reality check for yourself. For example, I know that the square root of 61 has to be less than the square root of 64. I chose 64 because I know that's a perfect square. Square root of 64 is plus or minus 8. And it has to be greater than a square root of 49, significantly greater, because that is the square root of, or the square of 7. So I would estimate this to be around 7.8, something closer to 8, but not quite 8. So it's a good way to kind of double check, because that should be longer than either one of the legs, because our hypotenuse is the longest leg. 7.8 is definitely bigger than 5, is definitely bigger than 6, but it's still reasonable, and you can always check that reason because it has to be less than 6 plus 5, the addition of both of those legs, so it's less than 7. So we can just leave this as our answer. So we now know that the interior diagonal of our cylinder is the square root of 61 meters, or you can estimate it, it's around 7.8 meters. Oh, no, this is our victory box. We found an answer, let's put it in rainbow. Wah! Bam. Okay, so that's one way that we can look at interior diagonals. The most common way that you're going to see it in 8th grade is with a rectangular prism, a box. So in this case, and now that definition should start really making sense, we're going to connect two corners of this box across to opposite faces. So I'm going to use orange again for that. I'm going to pull from this bottom left corner, and that means I need to go to the top right corner, but also in the back. Can't be on the same face. So I'm going all the way to this corner back there. So you can kind of imagine this stretches all the way through the box. It kind of goes all the way through the longest piece. That interior diagonal should always be that longest segment in here that we can make it go. Okay, different things. Now I'm kind of seeing, hey, I do see a right triangle in here. Actually, I'm not going to use blue because my sides are already blue. Let's use purple. Why not? So I see, hey, if I actually stretch all the way across just the diagonal of the bottom face, and then across this side right here, that is a right triangle, which is good. That means I'm getting towards something. I can use my right triangle theorem, where of course that interior diagonal is what we're going to call C. And then I already have right here, I know the length of this leg right here has to be 8 inches. But the length of this diagonal here, bigger than 18, less than 24, which is 18 plus 6. Don't know that one yet. So how do I find this guy right here? Well, I'm going to call it a certain thing because we have an unknown, and in math we sometimes call unknowns variables. Let's call it x. And then I see there's another right triangle that I can use to find this. So here we are. We're actually going to be applying our right triangle theorem twice. Let's get another color. Ooh, actually, let's use green. I see I can go across the bottom here. Here's where you kind of have to imagine you're looking down at the box. This still makes a right angle here. I know this leg is 6 inches. I know the leg at the bottom across here is 18 inches. Now I'm looking for that diagonal that's on the bottom face. That's my x. Let's set up our right triangle theorem. A squared plus b squared equals c squared. We're going to have to use it with that green and purple triangle first because it has one unknown. I can't use one equation to solve two unknowns. You need to have the same number of equations as you do have unknowns. So for my green triangle, I have one unknown, one equation. We're off to the races. I labeled those legs in green, so let's plug them in. 18 squared plus 6 squared is going to be equal to, that's my x length, which is another hypotenuse, squared. Let's evaluate. 18 squared is what, 324? Hope so. Plus 6 squared is 36, and that's going to be equal to x squared. Oh, right. Need to do a little bit of mini math here. I'm going to add these guys together. 324 plus 36, 10. Carry the 1. 1 plus 2 is 3, plus another 3 is 6. Don't need to carry anything. 360. All right, so 360 is going to be equal to my x squared. I'm going to do a real nifty-difty math teacher trick right here. I'm going to leave this. I'm not actually solving for x right now. And here's the reason. I'm about to plug this back in to my right triangle theorem, which means I need to square it. So I don't actually need to find x, I need to find x squared, and I have that. It's equal to 360. So this all the way across squared is 360. I'm ready to make my next right triangle theorem. So here we go, round 2. A squared plus b squared equals c squared. Now in this case I'm going to use, hey, a squared, which is going to be the same thing as x squared, plus c squared, or my next b squared, the other length of that side was 8 inches, so 8 squared, equals c squared, this time for realsies. I know x squared right from over here is 360, so let's go ahead and plug that in. I'm going to use green just to connect it back to that guy. Remember, 8 squared is 64. That's all equal to c squared. 360 plus 64, I'm going to swing up here so I get a little bit more room to play with. That is going to be 424 is equal to c squared. I actually care what c is, so in this case we are going to take the square root. Now remember, you could leave it as just the square root of 424. Because this is sort of my final answer, I'm not playing with it anymore, I might go ahead and say, alright, let's actually estimate where this is. So 424 I know is going to be a little bit more than 21, so you can kind of play from it from there. Just as long as you know how to do it, we are good. So c is up, oop, that's not a good approximately, is approximately 21.1 maybe. I hope that's right. Okay. Cool. So that is how we find our interior diagonal lengths. The big one that we're going to see a lot is just like example 2. Hope you have fun exploring. Remember that we're going to have to use our right triangle theorem often multiple times in order to deal with this. We're dealing with a 3-dimensional figure. Got to kind of play with it and visualize it. Even grabbing a prop, like you have a cylinder, grab a cup of water or something and say like, okay, what does this actually look like? Grab a box if you need a box to look at. I have my integer 24 game right here, so I might actually look at this and say, okay, how does this connect through? Where do I see it? Having actual props for some people is going to be really important. I do not have the strongest visuospatial reasoning skills, so having a prop for me is really important. I often fold up my pieces of paper in order to help me visualize. My artists, I know you're out there, you probably have really strong visuospatial reasoning skills because you practice it all the time. You might not need that. You might really be able to easily manipulate things in your head. The more you practice with it, the stronger you'll get. All right, happy exploring!